This is brought to you by the Alumni Association of PISJ-ES.
Continuing our lecture on Gay-Lussac's law, you should also remember that whenever we need to remove this proportionality sign, we always change this to an equals to sign and use a constant. So this proportionality turns into, this is known as a relationship and not an equation. Remember that, this is a relationship. However, if we want to turn it into an equation, we simply write P is equals to K times T. Now, K is constant for any gas. For the same fluid, it's constant. For the same, I should have written gas. I should have written fluid. For any fluid, for any substance, K is constant, and it's where volume is constant. So let's say I have a pressure of 150 atmospheres and a temperature of, let's say, 273 K. So what is my K here? This constant, this is. So simply just plug in the values. 150 is equals to K times 273. K is equals to 150 divided by 273 atmosphere per Kelvin. The units depend on what you're using here. So in this case, it's atmosphere per Kelvin. It can also be Pascal per Kelvin, Pascal per degree Celsius. That depends, but remember that the units should be consistent. As in, if you're using atmosphere pressure here, then you use it in the other situation as well. So this K will be constant here. Now, even if you change the pressure and the temperature changes because of that pressure, the K will remain constant. It will not change. So what happens? Let's say we have a situation here. I tell you that there is this container here, and the initial pressure was, let's say, 200 pascals, and the initial temperature was, let's say, 100 Kelvin. Well, and I changed the temperature to 250 Kelvin. Find out the final pressure. But it's very easy, because you know it's a simple relationship. P1 is equals to K times T1. Always remember that whenever you have a situation like this, always first of all find out the K. So it would be 200 is equals to K times 100. So 200 divided by 100 is equals to K, which gives me 2 Pascal per Kelvin. In this case, it's Pascal per Kelvin because you took this in Pascals and this one in Kelvin. So the units become Pascal per Kelvin. Now, this K will be the same, even in this relationship. So if you make a relationship for this, it would simply be P2 is equals to K times T2. And since the volume is constant and the fluid is constant, this is a fluid property. Since the gas is the same or the liquid is the same, even in the second situation, this K will not change. So you need to find out P2 is equals to 2 times 250. 2 times 250 is simply 500 pascals. So you find out the value. Also, there is an easier way to do this equation. Let's see our example here. Well, P1 is equals to 100 pascals. P2 is equals to let's say this is the unknown. T1 is equals to 250 Kelvin. T2 is equals to 500 Kelvin. So I changed the temperature. Let's see what the pressure is. So we can say, make an equation in P1 is equals to K times T1. Call this equation 1. Now change the subject of the formula and make this the subject. So this would be K is equals to P1 divided by T1. Now mark this as equation number 2. Now make an equation. So P2 is equals to K times T2. Now make an equation in K again, make K the subject of the formula. K is equals to P2 divided by T2. Mark this as equation number 3. Now you can see that since this K and this K are both the same thing, so you can just substitute the value of K here, which is P1 divided by T1 over here. So this would become P1 divided by P1 is equals to P2 divided by T2. This is your governing law, or let's say governing equation of this law. So whenever, this is the governing equation, whenever you know the final initial pressure and the final temperature, and the one of the values in the second situation, you can find out the second parameter here, temperature. If you know the second pressure, you can find out the second temperature. If you know the second temperature, you can find out the second pressure. Also, if you know the parameters for the second situation and one from the first situation, the initial pressure, let's say, you can find out the first temperature. Just change the subject as much as you want. So if you need it here, so we'll just make P2 the subject. So this will become P1, take this here, times T2 divided by T1. This would be equals to P2. So P1 is 100 times 500 divided by 250. So this would be, let me just find some space here, 100 P1 times T2 500 divided by 250. So 1s are, 2s are, 100 times 2 is simply 200 pascals. So this is your governing equation. P1 divided by T1 is equals to P2 divided by T2. So that is your situation. Let me just give you some intuitive feeling about this chapter here. Let's see, this is our applet here. These are the parameters here, the volume, temperature, pressure, and you can keep one of these constant at any point. Alright, these are the heavy species or the light species. We'll always be using the heavy species in this case. Right, this is the gravity, and when you in the later stages of this chapter, you might be able to see the effect of gravity on this. Well, let's keep our volume constant, and let's just introduce some pressure here. You can see there are some molecules coming in. Let's just increase. You can see here, this is the pressure meter here. It's increasing as I'm introducing more particles here. I think this is enough. Alright? Let's see what happens when I increase the temperature. Have a look at this. When I increase the temperature, they start moving faster and they start colliding faster. So what happens? The pressure increases, because you can see the collisions are more frequent. So the pressure increases. Now let me show this to you. Let me just decrease the temperature. I'm decreasing temperature, and you can see that the pressure is decreasing. Why is the pressure decreasing? Because the frequency of collision is decreasing. Their average kinetic energy is decreasing. So their velocities are decreasing. They're just coming to rest. You can see they're getting slower. So when particles are slower, pressure is low because they're not colliding as frequently. You can see, look at one of these particles, and they're taking much more time. If I add some heat here, you can see that their speed will increase, their average kinetic energy will increase, and so the frequency of collision will increase, and therefore you can see that the pressure is constantly increasing with the increase of temperature. Well, that is the scenario here. So you can see here, have a look. As soon as I'm releasing this, particles are moving out. The pressure is decreasing, there's a decrease in pressure, and so there's a decrease in temperature. As pressure decreases, temperature decreases. You can see this. I'm not cooling it. Then why is the temperature decreasing? Because the pressure is decreasing, the number of particles are decreasing, the average collisions with the walls are there. Now the collisions will be less frequent, and so their velocity will decrease eventually, and then their kinetic energy will decrease, and so their temperature will decrease. So let's see one more time. Heating it up and pressure increases. You can see, well, now if I just open the lid here, decreasing the pressure, and you can see the temperature decreases drastically. So guys, I hope you understood this, because this is a very important concept here. So if you have any problems, just let me know and write in the comment box. I'll reply to them. Thanks for watching guys. Stay tuned to it.